In this module, we're going to talk about gas laws for ideal gases. So starting out with the ideal gas law, you should have seen this before. PV equals nRT. P is the pressure of the gas, and the units of pressure are going to depend upon what value of R we use. I'll show you that in a second. V is the volume of the gas, and that has to be in liters. And it's how many moles of the gas we have. T is the temperature, and that must be in Kelvin. And R is the gas constant, which has different values depending. I'll show you in a second. So when do you use the ideal gas law? Almost every single time it's going to be, you know, 3 of these 4 variables and you need to find the 4th. Maybe you're given the pressure, the volume, and the temperature, and you need to find how many moles you have or anything. Next, okay, R. R has different values. These are the ones that you guys are most likely to need. There are others. 0.08206 liters atmospheres per Kelvin mole. If the pressure is in torr or millimeters of mercury, because they're the same, then you can use 62.36 liters torr per Kelvin mole, or liters millimeters of mercury per Kelvin mole. 8.314 joules per Kelvin mole. We see that a little bit later. 1.987 calories per Kelvin mole. So you should memorize these values of R along with their units. So now the combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. This is derived from the ideal gas law, and you use this in a different situation. When you have a gas and it has some value for these variables, and one or more of these variables changes value. So maybe you have a gas that has a certain pressure, volume, certain amount, and certain temperature, and let's say you change the temperature, okay? And maybe we want to find what the new pressure is. Well, what you do is anything that doesn't change, you just cross it off. So let's say you're not told anything about how much gas there is, or if it's added or taken away. So that doesn't change. You cross out N. And let's say the volume's constant. So you cross out V. What you have left is P1 over T1 equals P2 over T2. And all you do is you rearrange this, solving for whatever you want to find. So let's say the volume was constant and the number of moles was constant. So we cross those guys out. This is just an example. And you wanted to find at a new temperature what the new pressure is. So you just rearrange this, and P2 will be equal to P1 times T2 over T1. Plug these guys in, get your new pressure. Now watch out. With the combined gas law, for any of these variables except for temperature, they don't have to be in any specific units. Pressure could be in atmospheres, could be in pascals, what have you, as long as it's the same on both sides. But temperature always has to be in Kelvin no matter what. Watch out, that trips people up sometimes. So whatever pressure you were given here initially, that's the pressure that you would get. But a lot of times you're given temperature in Celsius, make sure you convert it to Kelvin here. All right, so that's the combined gas law. Now, STP stands for standard temperature and pressure. This is just an abbreviation, so memorize it. It's just another way of saying that the temperature is equal to 273.15 Kelvin exactly, and the pressure is exactly 1 atmosphere. So in a problem, you might just be told it's at STP. Just watch out and remember that that means that this is what the temperature is and this is what the pressure is. And that's all there is to that. Now here's another form of the ideal gas law. PM equals DRT, and this is really pretty cool. Okay, so here P is pressure, and again the units of pressure depend upon what units of R you use, just like before. M is the molar mass of the gas, grams per mole. D is the density of the gas. Now watch out, this is in grams per liter. We're really used to in chemistry dealing with grams per milliliter or grams per cubic centimeter. This is grams per liter. And T, again, is temperature in Kelvin. What's cool about this is that you can measure macroscopic properties. Pressure, that's pretty easy to measure in the lab. Density, just measure the mass and the volume, and you can do those. You need a balance and something to measure the volume. And the temperature, stick a thermometer in it. Measuring those macroscopic properties lets you calculate a microscopic property, the molar mass. So let me show you where that equation comes from. It comes from the ideal gas law, PV equals nRT. If you just realize that another way of writing N, the moles, is by taking the mass, that's a little m, in grams, divided by the molar mass in grams per mole. Right? Grams over moles is equal to moles. So instead of writing n, let's write little m over big M, where m is the mass in grams and m is the molar mass. Then rearrange it a little bit, bring the volume down here, molar mass up there. We get Pm equals m over VRT. But mass over volume, it's just the density. So that's where this comes from. Now let's look at an example. So let's see, we can figure out which homonuclear diatomic ideal gas. Okay, so the picture is this. We know that it's a homonuclear diatomic gas. Homonuclear just means it's the same atom. Diatomic means it's two atoms. So, it's one of those, the Hofbrinkel elements. And we measure its density, it's this many grams per liter. Measure the pressure, 424.1 torr, and the temperature, 23.2 degrees Celsius. We want to know which one it is. Well, here's the thing. If we can figure out what the molar mass of the gas is, knowing that it's diatomic, we just take the molar mass divided by 2, and that gives us the molar mass of the atoms. And look up on a periodic table and find that, and we'll have our answer. So we're going to use Pm equals dRT. Now, when do you use this equation? In a case like this, when you're dealing with something like the molar mass and the density. Those are kind of keys. So anyway, we want the molar mass because that'll let us get the density. So we rearrange this equation, dRT over P, plug in the density. Now I'm going to use 62.36 liters torr per Kelvin mole because we're given the pressure in torr. Now if you want to, you certainly can convert torrs to atmospheres and use 0.08206 liters atmospheres per Kelvin mole. Yeah, you get the same answer, but I'm kind of lazy, so I'll do it this way. And the temperature, 23.2 plus 273.15 should be 296.35. That has to be in Kelvin. And the pressure I'm going to keep in torr. Anyway, plugging in, we get 28.01 grams per mole. And we just take that and divide it by 2, and we get 14.01 or so. That's the molar mass of the nitrogen atom, so we know that this homonuclear diatomic gas is N2, or nitrogen.